In this third section of Chapter 1, we're going to look at the process of collecting sample data. When we collect data, it's really important that we pay attention to the method that we use to collect that data. We are going to be talking about the simple random sample as being the best of all the possible sampling techniques, also the hardest to kind of implement in practice. And the next statement in bold is really, really important. If sample data are not collected in an appropriate way, that the data can be so utterly useless that no amount of statistical torturing can salvage them. These are the words of the author, but I understand exactly what Mr. Triol is saying. The way I say it is, if you collect garbage, you can analyze the garbage to pieces. You can throw the best statistical techniques. You can put the best team on the job, but at the end, all there will be is processed garbage. So if you start with garbage data, there's just no way to make it right from there. So what you start out with is just as important as what you do with it to analyze it. You've probably heard of the term placebo. When studies are set up that involve a treatment, we want to adjust for the possible psychological effect of getting better because you think that you've been given something that is supposed to make you better. So a placebo is a non-treatment. It has no actual physical effect, but when given to certain individuals in a study group versus others individuals who are receiving the actual real treatment, we can make more valid comparisons as to the effectiveness of the treatment. Studies are usually labeled as either observational studies or experiments. There is a big difference between the two. Observational studies are passive. Things are happening and the researcher is recording what is naturally occurring. The researcher does not have an active role in the environment of the study and is not trying to influence that environment. Kind of think of it as looking into a room from behind one of those frosted mirrors where you can see them but they can't see you. So observational studies have no involvement in the study itself on the part of the researcher. Experiments, on the other hand, there is some active role that the experimenter, the researcher, is involved in. So an experiment involves a treatment, and that treatment is what is being studied in terms of its effectiveness. So whereas observational studies, there's no involvement in the environment of the study on the part of the researcher, experiments by design have some sort of intervention called a treatment that we're trying to find the effects of. In an experiment, whoever is receiving the treatment is referred to as an experimental unit. That's a bit of a formal title. They're more commonly called the subjects of the experiment. The subjects are the people who are receiving the treatment and that we're studying in terms of the effects of the treatment. And then, as we said earlier, an observational study is more passive. There is no active involvement on the part of the researcher. There is no attempt to influence the environment that the study is taking place in. Here is an example of an observational study. It's actually a pretty interesting one. Past data leads us to conclude that ice cream causes drownings. Interesting. Ice cream causes drownings. Where does this come from? Well, we have data showing that as ice cream sales go up, then the number of drownings also tends to go up. So more ice cream sales, means more drownings. So a conclusion is, well, ice cream causes drownings. Of course, we do not believe this is the case. What we have here is something working in the background that is a lurking variable. Basically, people tend to consume more ice cream in the hotter times of the year, right, when the temperature is higher. And it is also when people go swimming more, right, when the temperatures are higher and the water is a little bit more comfortable. So ice cream consumption or ice cream sales and the number of drownings, they are related, but it's not a cause and effect relationship. They are both being influenced by that lurking variable of higher temperatures. And of course, the more people who swim, unfortunately, the number of drownings does increase as well. So we're going to talk about this in more detail in future chapters, but just because there is a relationship between two variables does not give us the automatic conclusion that one causes the other. The only way to really establish a cause and effect relationship is to conduct an experiment. This slide makes me giggle a little bit because it says if we want to prove that ice cream sales causes drownings, then we should do an experiment. So what they're suggesting is we set up an experiment where one group of people consume the ice cream, the other group does not, and then we compare the number of drownings for the two groups. Well, I don't think this makes a good experiment. I think there's a lot of violations here to the safety of human beings, but the point is the only way to even hope to establish a causal relationship is through an experiment. And that actually is the challenge. If there are some moral hurdles to doing an experiment, then you're not going to be able to establish that cause and effect relationship. Let's think of cigarettes, for example. So it has long been recorded that people who smoke tobacco, cigarettes, tend to have higher incidences of cancer. And this is decades and decades and decades of data. So why has it taken so long for us to be able to say smoking cigarettes causes cancer? Well, it's because of the moral dilemma of, can we really designate a group of people that we're going to designate as the treatment group, and we say, okay, you guys need to chain smoke for the next amount, whatever the amount of time is, and we're going to see if you develop more cancer. And then we're going to have another group that does not smoke, and then we're going to look at the cancer rates there. There definitely is an ethical violation in doing that, especially if there's a predicted harm involved. So that's one of the challenges in statistics, is that we cannot establish a causal relationship, a cause and effect relationship, unless the data is coming from an experiment. And there are many things that we believe are cause and effect relationships that we simply can't say so, because to put together an experiment would definitely violate some ethical concerns. A well-designed experiment should be one that is easily replicated. We should have enough information about how an experiment was carried out that another researcher can take those notes and replicate the experiment. When we are replicating an experiment, we want to make sure that we have large enough samples so that those results can be used to generalize to the larger population. So we're going to look at the effect of sample size on the type of conclusions that we can draw and how confident we are in those conclusions in another chapter. In an experiment, blinding refers to a technique in which the person participating in the experiment doesn't know what they're receiving. They don't know if they are receiving the true treatment or if they're receiving a placebo. For obvious reasons, we want to withhold this information from the subject, because otherwise the role of the placebo is kind of nullified. Blinding is a way to get around that placebo effect of people reporting that they feel better after receiving a treatment when in fact what they received had no medical value. Usually we call this a sugar pill. It looks medicinal, it looks official, but it's nothing more than the equivalent of a Tic Tac. Double blinding, on the other hand, refers to not only the subject being kept in the dark about what he or she is receiving, but also the person administering the treatment or the placebo is kept in the dark about what they're giving. Of course, there's some way to tabulate who's getting what, because otherwise we wouldn't be able to study the results very well. But what this is intended to do is to also remove the possibility that the person giving out the treatment or giving out the placebo, that they influence the subject in any way. For example, if I know that I'm giving you the real treatment, the real experimental drug, I might say, this is likely to make you better, we're really hopeful this works, and I may unintentionally, give you information that may influence how you respond to it. And the same goes if I know I'm giving you a placebo, I'll be like, okay, don't feel pressure to tell me if you feel better, you may not feel anything. So double blinding just eliminates the possible introduction of some bias on behalf of the researcher or the person administering the treatment or placebo. In this course, we're going to talk quite a bit about randomization. Anytime that we are able to do anything at random, we are hopefully removing bias and removing skewed results. And the reason is, when we use true randomization, true random selection, we have the best chance of generalizing to the entire population. Anytime we make selections that are not truly random, we are introducing some possible errors, we are introducing some possible biases. We are now going to start going through the various sampling techniques, and we're going to start with what statisticians consider to be the best technique, in the sense that it gives us the best possibility that our sample looks like the population that we're trying to learn about. So remember, a sample is a subset of the population of interest. It is a group within that larger group. We want that smaller group to just look like a mini version of the larger group. We don't want it to look different. So the simple random sampling technique is, of all the techniques that we're going to talk about, the one that gives us the best chance of that sample representing the population that it comes from. The way it is drawn is that if we were to choose a certain number of subjects, and let's call that number n, if we were to choose n subjects or n people from the population in such a way that not only every individual has a chance of being part of the sample, but any group of that size has an equal chance of being chosen. So it's not just about every individual being able to make it into the sample, but once an individual is chosen for the sample, all the others that are left can also be part of that group. It may not make a lot of sense now, but we're going to see through some of the other sampling techniques in future slides where each individual can make it into the sample, but then once an individual makes it into a sample, there's certain other individuals left that no longer can be part of the sample. So that second piece is really distinguishing for this technique. Let's take a look at the next one. This one is called systematic sampling, and the way that this is done is that we choose a starting point, and before we choose a starting point, all of the people or objects in the population that we're trying to study, they are put in some sort of order, be it a list, and we choose a place to start at random, and then from that starting point, we're going to jump to every kth one in the list. So for example, let's say that we have 30 students in our class and they're lined up in a line, student 1, student 2, student 3, etc., all the way to student 30, and I choose at random that I'm going to start with student number 5. And to gather my sample, I'm going to jump to every third student thereafter. So from student number 5, I'm going to jump 3 people and go to student number 8. And then from student number 8, I'm going to go to student number 11, and then student number 14. And those are the students who are going to be part of my sample. This is a very common technique in manufacturing. Think about quality control. If you are in manufacturing and you've got items coming out of an assembly line, let's just say soda bottles, it would be very time consuming to do a quality check on each and every soda bottle that came out, especially because manufacturing tends to be very, very fast. But you do want to have quality control, because if there's a defect in the process, you definitely don't want to wait until the end of a big production day to figure out that you have 1 million soda bottles that have a defect. So typically what happens in manufacturing is that they choose every, let's say, 100th item to inspect, or maybe every 1,000th item. So not every single product is being checked, but it's being checked periodically, so that if that, let's say that 100th product had a defect, now they only have to go back 100 products in front of it, because 100 products ago we had a good functioning system. We kind of know where to narrow down where that error started occurring. So this is called systematic sampling. It does involve some random selection in the sense that we randomly choose where to start, but think back to my earlier comment. If in this diagram I'm choosing the third vehicle, and I'm going to jump to every third vehicle from there, now that 4th and 5th car no longer have a chance of making it into the sample. So you see that while the 4th and the 5th car could have been part of the sample initially, because I could have begun my sampling with either one of those as my first car, once I choose a starting point, there are certain cars that can no longer be part of the sample. So each individual car can make it into the sample initially, but once I choose a starting point, certain ones are cut out. Convenience sampling refers to gathering data that's just easy to get to. Surveys are a good example of convenience sampling. If I were to stand outside, let's just say the library on campus, and I just asked a survey question to people as they came out of the library, that would be an example of convenience sampling, because it is very little effort on my part. They're basically just walking out and coming right to me. If you've ever visited the theme parks here in Central Florida, you may have run into a staff member from the theme park where they're walking around with their little clipboards, and they're just kind of hiding around the corner waiting for guests of the park to just turn that corner, and then they come and ask you some questions. Well, that certainly is convenience sampling. It's easy to get. Unfortunately, the convenience comes at a price. The data that comes from this type of technique tends to be rather skewed, tends to be rather biased, and I think for obvious reasons you can see why convenience sampling doesn't give us good confidence that the sample we end up with represents the entire population of interest. So for example, the people who turn a specific corner at a theme park, may not represent those guests who don't even visit that part of the theme park at all. You know, imagine if that part of the theme park was catered to small children. Well, guests who don't have small children may opt to not go there at all. So you are getting a sample, but there's really not a very good chance that that sample is going to be truly representative of the entire population of interest. Stratified sampling is quite interesting. Basically, the word stratified comes from the word strata, which is plural for stratum, and stratum you can just think of as a group. So stratified sampling is also referred to as group sampling. The way that this works is that the population is naturally separated into different subgroups. It could be two, it could be many more. These subgroups are called the strata. Here in this slide, you have two very naturally occurring groups, men versus women. If you're sampling, let's say, a high school, maybe you have four groups. Maybe you have freshmen, sophomores, juniors, and seniors. So you can see that these examples tell us that there's some natural grouping happening in the population. Now, those naturally occurring groups may have some differences between them. So for example, the freshman group may have some differences from the senior group, and I think we would agree that there are some. So the idea behind stratified sampling is that we identify these naturally occurring groups from the beginning of the sampling process, and then what we want to do is we want to randomly select from within these naturally occurring groups. So we want the sample to, include people from all of these different subgroups in their respective representative percentages. For example, if we had, let's say, a particular business that consisted of 35% men, 65% of the employees are women, so it's kind of a woman-heavy kind of business, we would want to make sure a sample included roughly 35% men and 65% women. So we would randomly choose men for our sample, we would randomly choose women for our sample, we would try to respect the percentages. Cluster sampling is a little different. It does involve groups, and these groups or clusters are also naturally occurring, but unlike strata, these groups tend to occur by geography, by how close they are to each other. Let's go back to the school example. If I was talking about cluster sampling, I could have, let's say, a school district. Let's say a particular school district had, let's just say 30 schools in the district. And we want to send some researchers into these schools. And instead of choosing students from all 30 of the schools in the district, what we would do is perhaps we chose 5 entire schools from the district. And so each one of these 5 schools would be considered a cluster. Notice that the people in the school are naturally clustered together by geography because they're in the same school. And so it makes the research team able to get to them more easily, because now instead of having to visit people in all 30 schools, they only have to send the research team into these 5 schools. So as you can see here in the graphic, this happens a lot with zip code sampling. Instead of, let's say we wanted to know something about people in Florida. Well, instead of having to send researchers into all parts of Florida, we could randomly select certain counties, or we could randomly select certain zip codes, and then we could send our research teams within those areas. Now, cluster sampling, once we choose those clusters, we would not do any additional breakdown. We would actually cover the entire cluster. So in the example of the district that has 30 schools and our sample consists of 5 schools, we would kind of conduct a census within each of those 5 schools. We would study every part of the population within those 5 schools. Multi-stage sampling refers to a mix and match of the sampling methods that we talked about. For example, if we back up one slide to cluster sampling, let's say that we selected at random some clusters from within a population, and then within those clusters, instead of doing an entire census, we sampled again. And it could be anything, systematic sampling, for instance. Let's say we had a student list based on student ID numbers. So if we first start with a cluster, and within that cluster we choose a systematic sample, that now is involving more than one technique, and we refer to this as multi-stage sampling. Regardless of which sampling technique is used, there's always the possibility that the sample you end up with is not representative of the population, and that could be due to some error, or it could just be due to chance. We refer to this as the errors in the process. Sampling error, for instance, occurs when the sample has been selected with a random method, but there's a discrepancy between the sample result and the true population result. We're going to spend a lot more time looking at sampling errors as we get into the later chapters of this course and we start looking at hypothesis testing. But just be aware that even if we put the best technique into action, there is always a chance that our sample looks a little different than what our entire population looks like, and so when we make those generalizations, they may not be entirely accurate. And finally, this last slide talks about other types of sampling errors. We're not going to need to dig into these right now. Just be aware that we always aim to get the best possible sample. Remember what I said earlier in this video, if you start with garbage, you can throw the best tools at it, and at the end all you're going to get is processed garbage. So taking a look at sampling techniques really opens our eyes to being very critical about what kind of data we start with, but just know that even if we try to use the best techniques to get good data, we may not necessarily have a sample that really looks like the population that we're trying to learn about. There's always going to be that chance that there are some differences. And with this, we'll end this video, and we are ready to move on to Chapter 2.